what we are going to do, we are going to go through all the papers, okay, that I uploaded in Google Classroom. And for each of the paper, we are going to see the statistic that is involved in each of the paper. Okay, so I'll leave that what paper should we have a look first. Okay, and then I'll give you guys something like 5 minutes or something. You don't have to read the paper, just to see what are the statistic that is involved. So basically I'll give the first paper as an example first, okay, as an example. So the rest you can start sort of like trying to identify and then to see, okay, for yourself, and then we are going to discuss about that. So I hope that everyone is having all 4 papers with you now, okay, and if you do, okay, this would be the first paper that I will give examples of, and then for the rest I'll give you some time to figure things out yourself, and before we're going to discuss, okay, each paper. So the first paper, okay, is the one from Biotechnology report, and it's about kinetic analysis and modeling of alkaline production. So this paper, even though it's the paper itself say it's kinetic analysis, there's a lot of statistic that involve, and as you see that when we see the word kinetic analysis, is basically, and modeling is basically trying to fit the curve, okay. So in this paper, okay, if you go through, you don't have to read the paper like I told you, okay. If you go through, you'll see that, okay, they are having some kind of model that they are going to use. So they are doing experiment and fit the data, okay, and they have the model for substrate, for product, and also for growth, okay. And so you know that, okay, one thing that you can identify is trying to find about the statistic is through the materials and method, and in results and discussion, okay. For example, in this type of paper, I know already that they are going to do like kinetic simulation and modeling, okay. So I know that they are going to do graph fitting. Remember the graph fitting, the lecture that we do earlier, okay. If you're going to 2.6, they are talking about model parameters, estimation, and validation. So basically what they are doing is they are doing the experiment and finding the models, which are the equations that they talked earlier, and they are trying to fit the experimental data to those models. And in order for them to fit the data, they have to know like parameters, the unknown parameters like y-axis, alpha, beta, and ks, mu max. That type of stuff are the parameters that they have to vary to get to the point. The detail, like how they do it, actually it will be covered in next semester when if you enrolled in biochemical engineering lab, because we have the graph fitting things, the modeling things in. Okay, so one thing that you probably see at this point, okay, I don't know whether you see it, is the determination coefficient mathematical expression, or the R square. Okay, so that's one thing that you see. So it involves R square. Okay, it involves the word mean square errors. So thinking about statistic that we did for descriptive statistic, when I say something about graph fitting, okay, so it is used to test deviation of experimental data obtained concerning data from the simulation, blah 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 blah. And another word that you probably come across is Duncan multiple comparison. So that's when something comparison and you see the word Duncan, that is something you have to do with the statistic, okay, with the confidence level of 95%. So you see, even though it's modeling paper, it's still like having some kinetics, that having some statistic that goes with it. And they actually see that they say that using Duncan multiple comparison with the confidence level of 95%, so you know it's alpha equal to 0.05. Okay, intended to determine whether there were or not any significant difference between value obtained among different substrates. So they are comparing things with the substrates and to see if there's any different, okay, in the value obtained with the substrate at confidence level of 95%. So they are doing some kind of comparison based on statistic as well. And they also have the formula to calculate R square. So that's the R square. And if you see this type of paper, then you know that, okay, yi and fi is what, okay. So sometimes they use a different symbol, okay. So they said here that yi are the model data, and normally when we have model data, we have y hatch, right? We have y hatch, which is not in this case, but y bar is the average, all right? Yi is the experimental data, so that's correspond to what we had before, okay? And they use mean square errors, okay? They use mean square errors, so this is the formula to calculate the mean square errors. And then you see that it is the difference between the experimental data, okay, and what you get from the model. So by seeing this, you know that they probably use the mean square errors to make it minimum, so that they can have the best fitting curve happen. Okay, so that is some part, okay, that is involved statistic in this paper. Okay, so going on to the next section on the right, okay, there's nothing there, and this is the normal thing you see with the kinetic modeling stuff, okay. And you see that they want to compare the parameters values because they are using different type of media, right? They use glucose and they use lactose down here, okay. So they want to compare whether the values they get from glucose and lactose for the parameters are different. So they're doing some type of comparison. Okay, so that's how the point here are the experimental data. Okay, and the kinetic parameters, let me see later on. Okay, so that is the experimental data, but it's not the curve fitting thing yet. Okay, one thing that you see in this graph, okay, I hope you see like what I see, is that you have an error bar here. Okay, so each point has an error bar, so you know that they are doing some sort of repeats. Okay, and this error bar, some people just using SD, some people using like the PL errors, so it's the difference from the average. Okay, and see that they said vertical bar represent standard deviation. So in this study, they use standard deviation. So at least you know that up to this point, okay, up to this point, the stat that involve, okay, the stat that involve is the calculation of R square, is the calculation of mean square errors. And basically this is for modeling. Okay, so think about your thesis and the assignments that you are given. Okay, at this point, if anyone has any question, you just type the chat or open the microphone, okay, or raise your hand or whatever, so I can stop and then answer your question. Okay, and okay, back to here. And apart from these 2 points, okay, we have the stat that involve also has to be an average, right? You can't find standard deviation if you don't have the average values. And of course, you have to calculate the average value if you want to calculate the R square things. Okay, so fourth one is standard deviation. Okay, so this is for calculating what for general data analysis. Okay. So this is up to this point only. Okay, up to this point you have a lot of stats involved already. So think about your work. Okay, think about your work, whether I need to do this, whether I need to do that. You might end up having just average and standard deviation. That's okay too. Okay, scroll down. Okay, scroll down a little bit, you'll see this table. Okay, scroll down a little bit, you see this table. You see that in this table, let me expand it a little bit. Okay, so you see this table, and you see that in this table there were numbers of values, right? So they are doing modeling, and they get the kinetic parameters already. Okay, they get kinetics parameters using different carbon sources. Okay, and the carbon sources is they have glucose, they have lactose. W, I don't remember what it is. Let's see what they have for W. They probably have in material method, but so they have 4 type of carbon source, and they said earlier that they are going to compare, right, the kinetic parameters that they get by using Duncan multiple range test. Okay, and at 95% confident level. So that means that they are doing this at 0.05. Okay, so basically when they said they use Duncan multiple range test, so basically you are doing t-test. Okay, you are doing t-test, and then you are actually ranking Duncan will help if you're using SPSS before you use Duncan test as your post hoc test. You see that they are grouping it for you, which one is not significant, not significantly different, which one are significantly different. So it's actually a Duncan multiple range test, and you probably need to know that it is t-test. Okay, so they are comparing each category of the kinetic parameter and see whether they are different significantly. So the number 5, okay, the number 5 in your stat test is the, you can say it Duncan test, or it could be like, you can also use t-test in this case, okay, to see this is to test a difference in mean values. Okay. So what they have here is, okay, for those of you who might not be familiar with the descriptive things here, okay, let's say let's see for mu-max, okay. So for mu-max, they are comparing the mean, okay. This is quite obvious. Different letters, okay, will say that they are individually different. Let me give you other example. Okay, let me give you an example of y-axis. Okay, when you compare the mean, you know that y-axis for glucose is 0.255, for lactose is 0.267, 0.239, 0.273. Okay, so basically if you look at the number alone, they are sort of like different. Okay, you might just say that they are different because they are different numbers, but statistically, if you are doing repeats and then you have this stuff and then you compare the values that you get, you see that by statistic, this value and that value is not different because they are with the A above, okay? And these values are different from the two values because they have the B on top there, okay? So what about this one, which having A and B? Having A and B means, okay, means that they are not different from A, also not different from B. So basically, they are placed in another category. And if you are ranking them, you see that A is the highest average values, and then AB, and then B. So this is how you are comparing mean, and it's easy for you because the program just does this for you. The program will not give you A, B, and A, B, something like this, but it's the details that you have to go and see and learn how to put all those numbers in the tables like this if you want to use this method. Okay. All right, so what else that we have for this paper? All right, okay, up until here doesn't seem like then extra things that happen for the statistic used in this paper. Like this one, I just want to show this one. This one is the modeling line, I think. Yeah, the line is a model that they have with the parameters that they have in that table, and the dot is actually the experimental data. You see that if you're doing modeling, the line doesn't really go through the dots that perfectly. Okay, so how they do that is, I'm pretty sure that they try to minimize the MSE, the mean square errors there. Okay, let's see more things. Okay, I think that is all for this paper. Okay, that is all for this paper. So with this paper alone, okay, with this paper alone, you are having like 5 major stats that involve. Okay, so you have R square and mean square errors. They are using in modeling. Okay, R square, see how fit the model to the data. MSC is for finding like the best fit line. Okay, after that you have the average and standard deviation, which is the general data analysis. Then there were some these are descriptive statistics. You see that? And also you have inferential statistics where you do t-test and Duncan test to see the difference in the mean values of the parameters. So this is how you should be able to analyze this stuff, and by doing so, it should enable you to think about your own work of what type of stat that you will be doing. Okay, so that is the first example. That is the first example. The next example that I want you to spend some time doing what I'm suggesting in this doing what I'm suggesting in this paper to other papers. Okay, I think we take about like 5 minutes. Okay, the second paper that I want you to have a look is this paper. Okay, everyone has this. Okay, everyone has this paper with you. Okay, I'll give you something like 5 minutes. Okay, just go through the paper, and maybe we help each other out in class that what do you say. Okay, I accept your answer and question in Thai, and if necessarily I will translate it to English so that our friend will understand as well. But we can do this in Thai, and I mean in dual language. Okay, so let's take like 5 minutes, and then we'll come back and see how do you get through. I'll mainly ask you and guided you, but I want you to say something or have some activities here. All right, okay. Come back at about 1:30. I'll come back at about 1:30, and then we continue with this paper, okay? Okay. Now, let's come back. Right, I just want to hear from you. What do you see in this paper about the statistic that is used in this paper? Anyone wants any goes first? You can actually type down, and we'll see where it is. Okay, so think of it as a paper analysis as well. So it's pretty important for us too. Okay, right. If no one has any response, let's see. Okay, actually with this paper, the first thing you see, even from the abstract, you see it already like that. See that? So that means that it has to involve the average values, correct? So it has to involve the average values. And for the plus and minus stuff, I'm not, we can't say at the moment. It could be errors or it could be standard deviation. In that case, we scroll down and see, okay, whether they use, okay, so they do standard, they have a statistical analysis, okay? So they use design expert software for experimental design optimization. They use Minitab for screening variable. Accuracy of the model evaluated with p-test. P-test is actually the f-test with the p-values. Determination of coefficient lack of fit, blah, 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 represent at p less than 0.5. I think this is f-test rather than p-test. Okay, they are, see that they are doing it at 3 different p-values. See? 0.05, 0.01, and 0.001. Okay, they said all experiments done 3 times. Data proceed with Microsoft Excel. All graph, all values were reported as mean and standard deviation. Okay, so that means that the stat is average value, yes, and number 2, they have to do a standard deviation. Okay, so if the paper is having a statistic analysis, and this paper is actually very generous with the with the detail, okay, so you can actually extract, okay, in this case I can extract, and then we'll see where things are for each of these. Okay, so they have p-test. Okay, they have p-test, which I think is actually an f-test rather than p-test. Okay, and they have calculating the r-square. Okay, and they do many different tests. So this is for the modeling. Okay, so for the model, you might think, hey, how come it's a model? Because it's a optimization things. Okay, and they said that apart from that, they are using 2 key tests for comparison of the mean. See that before in the paper before they use Duncan. Okay, but for this paper they use 2 keys to compare the difference. Okay, so that's how it is for this paper. Okay, to explain more like why the modeling is coming into play, because they are saying that optimization, okay, they are saying optimization. So let's scroll down here. You see that in the part that says optimization, okay, the part that says optimization, they are interested in 4 variables. Okay, and normally they are with optimization, like and Box-Benken design, you know immediately that they have to use response surface methodology, and in order to do so, to get the optimum values, you have to fit those data into a model. And in this study, they use second order polynomial model. Okay, and the equation is that. So whenever you see the response surface graph, okay, it has to come from the mathematical equation of some type. Okay, and if you see the curve, you know that it has to be like polynomial, because linear model will not give you curve. If it is curve, it has to be like at least second order polynomial model, and you know that it is polynomial polynomial model because it has the square things here. So this is in previous paper, they are doing modeling, but it's a kinetic modeling. But in order to do optimization, you have to fit the curve as well. Okay, that's why when you have ANOVA tables, you have R square, you have so many tests. Okay, and in this paper, okay, in this paper, they use desirability index to select the optimized parameters. So I'm pretty sure that DI is since the desirability factor is from 0 to 1, normally the values closer to 1 is the thing that you say is the best fit. Okay, so basically it's in this paper they're using DI instead of the mean square errors in another case. Okay, but like for the previous paper, when they use the mean square errors, and I said that they probably like trying to minimize them. So it fits into the category of graph fitting, that we use the Q values. Remember, the Q values is trying to minimize the residual errors to be at minimum to find the best fit line. Okay, so this is another case here. Okay, and let's see next. Okay, we will come back to this highlight a little bit later. Okay, so in this study, they actually are trying to screen. They are trying to screen for the factors first, and they are doing screening with Paglet-Berman design. Okay, so it's another experimental design which only, I think, is concerned only the minimum and the minimum, the two values, like the lower value and the higher value. So to see to screen first which factor is important before you actually doing the response surface methodology. Okay, and in this case they use Paglet-Berman design. Okay, so they use Paglet-Berman design, and this design has 3 levels, and they use first order polynomial again to determine things. So whenever you see this, it is the first order polynomial is basically a sort of linear model because it's a linear coefficient. Okay, right. So in the first stage, they are using the stat from the beginning. Okay, they're using the stat from the beginning, and the stat that they use. Okay, you see, normal in Paglet-Berman design, you are trying to see which factor is significant. Normally they give tables, but in this study they don't use table, they use graph. Okay, so you normally see which factor is significant or is important for you to further investigate. And you see that the factor can be positive effect or negative effect, depends on the side that you get. But the important points that I want you to see here is the t values. Okay, you see that it's a t value of effect. Okay, so they calculate the effect of each parameter. So that's actually another stats thing that they do. So I would say here that you have to calculate. I would say in this case I would say it's what is the name again? Paglet-Berman design. Okay. So the stat that involved is Paglet-Berman design. Okay, and then they are using the, parallel charge is just another way to display the results. Okay, the point is that you see that there are t values here. Okay, so you know that you have to have t-test. Okay, you have to have t-test because you have to calculate t values. Okay, and now you have t value limited line, and they are all at 2.035 because they are doing just one alpha, and they have another line called Bonferroni limited line. Okay, the important one is t values limited line, and it is the test because it says here, okay, look at the highlight here. It said the effect of parameters on response, blah blah blah. It said it's shown in parallel charge that we just saw earlier. Okay, this study obtained two limited line, which is Bonferroni limited line and t-value limited line. So it's the t values. So it's the t values that is the stat values that is calculated, okay, for each of the parameters, and the t values of effect above this were considered extremely significant, blah blah blah, were considered significant, and below t values limited line were considered non-significant. So if you think about this, okay, it's more or less like what we had talked about earlier. Okay, that remember that if we have like t distribution, okay, we have t distribution, and it seems like in this case the limiting values here, if they do one tail, okay, if they do one tail, okay, seems like the limiting here is 2.035. Okay, and what they said there is that if the t values, okay, if the t values that they calculate is below the t limited line, is non-significant. Okay, so come back to these pictures. Okay, if the t values, so for example, okay, let's see this graph. Okay, for example, the t values line is here. Okay, so anything that below this line will have the values less than 2.035. So like this one is 1.5, this one is about 1.5, this one is very low at about 0.1. So all of these four graphs, okay, have the t values. So like to the left hand side, see, it could be here. Okay, maybe this one is 1.5, maybe that one is 0.02, okay, for some or something here. So you see that it is not the area. So in this area is accepting H naught, right? so it is saying there's not much different when changing the level of these parameters. Okay, and the t value of that you accepting is 0. Okay, so accepting the except for the pH where the values is higher than 0.35, so it's about 2.6. So it is somewhere here about 2.6 here. So it belongs to the part where you reject edge node. So that means that changing the values of this make things different. So this is how it is and how statistic comes into play. And if you understand about doing statistic tests, okay, of course you have to go. I mean to get the correct interpretation, you have to go to see that, hey, what is the null hypothesis and alternative hypothesis for this specific kind of test. Okay, in order to interpret the result correctly. But like, this is what I show you just now is the basic things about accepting edge node and rejecting edge node, and just show you how things can be presented in different way. All right, so what's next? Okay, let me erase this part first. Okay, what's next in this paper? What next in this paper goes down to, okay, you have Box-Benken design tables here. You know that you have the average values and then plus minus SD here. Okay, so they're doing pretty extensive thing. Okay, normally when you are doing like the Box-Benken design things, you don't have to do the repeats because the center point are actually representing the errors from doing repeat things already. Okay, but I'm not very sure whether they have that, but anyway, so that's another details that we are not covering at the moment. Okay, now scroll down and you see the analysis of variance, and you see all the tests. See, that is not a P test, it's an F test because it's the F values here. Okay, the F values here, that's the F test. So before they actually get these F values, actually there were some other columns as well, but I think with this one, they are looking at 3 different response. Okay, is this response the 5 CQA yield, the fermentation efficiency, and the antioxidant activities. That is why they just shorten everything up and then just show the F values for each of the term, for each of the response. Okay, but you can see from these tables that they are doing F test. Okay, so it's Anova analysis. So if it's Anova analysis, you know it is the F test. Okay, and it's Anova analysis of what? Okay, it's Anova analysis of the model parameters. Okay, the model parameters. So that's why with this work, you have the optimization for 3 of the response. So you have 3 different equation to explain the response, like you see down here. Okay, and okay, so each term, okay, you see that the test that they do, the first one is the model. Okay, so if you see something like this, whenever you see the p values, is one test. Okay, so with this one, how many tests? All right, for this response, you have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16. Okay, for this one you have 16 different tests. Okay, 16 different tests in this response alone. Okay, so what are the tests? The first is testing the model. Okay, testing the model. So testing the model means that we have to find that the model testing, what are the edge node and edge alternative, HA or H1 of this test. Okay, and once you know what are the edge node and edge alternative for this test, you know that, okay, so if p-value is very small, so in this case p-value is less than 0.05, if they do the test at 5%, at alpha 0.05, so that means that you accepting edge node, you rejecting edge node, right? You rejecting edge node, and that means what? Depending on what the edge node and HA is. Okay. And also for each individual items here, so they just want to see whether these individual items, you see that each equation here has an x1, x2, x3, x4, okay, which are these four. Okay, they have x1, x2, x1, x3, x1, x4, and all the interaction are here, and then you have like the square term here. Okay, so those are here. So the test here is just the test to see that it is the test to see that each of the term, okay, each of the term, if x1 is actually affecting the yield, x2 affecting the yield, is x3 affecting the yield, x4 affecting the yield, or x23 affecting the yield. These are the tests that they are doing in the ANOVA, okay, and we just translated into the parameters here into the factors that we use in the experiment. So basically, if you are, okay, let me, oh no, I don't want to clear all of it. I just want to erase some of this stuff. Okay, so if you are looking at this part, okay, if you are looking at this part, okay, this part alone, you might actually, it says that, okay, x1 wouldn't have an effect, right? Because the p-values is 0.6. So again, if we are looking at this, these are F tests, okay, and F test, I'm not sure F critical here is what, and if this is the area of 0.05, right, alpha of 0.05. So if it is 0.6, it is beyond 0.05 to the is less than 0.05 to the left here. So that means you're accepting edge node, and accepting edge node means that there's no change in response when temperature changes. That means that the temperature is not significant. So looking at this one, okay, actually it says that this x1, okay, whatever values you put in this x1 doesn't really affect the yield, okay, but when we translate it in when we do the translation, we say that temperature doesn't have an effect. It doesn't have an effect because in this equation it doesn't have an effect on the y values. Okay, and the rest, the pH, incubation time, and liquid to solid ratio actually has an effect on the response. So we say that it has effect to whatever we are interested in. Okay, and have a look at some other values. Okay, let's have a look at these values here. Okay, where P is equal to 0.0016. Okay, so if you remember that this paper says that they are doing alpha equal to 0.05, alpha equal to 0.001, and alpha equal to 0.0001. Okay, you see that 0.0016. Okay, if you are doing the test at alpha 0.005 or at 95% confidence level, this one is significant, right? Because it's less than 0.005. Okay. But if you compare 0.0016 to 0.001, this one is higher than these second values. Okay, so that means that if you test at alpha of 0.001, this interaction BC becomes insignificant. Okay, it's significant in the first value of alpha, but it's not significant in here, and it's not significant in here. So not significant means that because sorry, hold on. Because basically what happened here is that you definitely have the same you have the same distribution curve, but you just cut it differently. Like if this area would be for alpha of 0.0001, okay, and that area, including the red area, would be alpha equals 0.001. This is not to scale, okay? I just want you to see the difference. And that area, the yellow area plus the green area and the red area, would be alpha of 0.005. 0.05. Okay. So that means that testing the same one at different alpha level will give you could give you a different results. Okay, could give you a different conclusion. That's how it goes with statistics. Okay. In this graph, not this graph, in this table, I'm sorry, there were some other statistic tests that is going on as well. Okay, just let me wipe down this mess here first. Okay, so another thing that you might see here is the like I told you. Okay, so each one will have their own edge node and edge A, including this one, the lack of fit, and the model and the lack of fit. So it's if you really want to understand what it is, you should go and you can search the internet for this. There are so many pages that explain what are the statistic tests for the edge node and edge A for model and the lack of fit, and why by rejecting or accepting the edge node of that, why you interpret the results like that. All right, and apart from the statistic test, okay, apart from the statistic test, we have R-square. Okay, we have R-square. Remember the R-square? In the lecture, we talked about R-square and adjusted R-square, right? This one also have a predicted R-square. So it's three different R-square tells you different thing. In short, like R-square give you like how fit the data is with the model. Adjusted R-square is to see if your model has excessive terms that you can drop it off, and predicted R-square is basically how well you can use this model to predict your data. So it's three different things, okay? And this thing can be found. I mean, you can find more information on the internet as well. I love this. I love this generation. You have so many like source of information, okay? So that is about the ANOVA alone and about the optimization alone. Okay. All right, what else is in this paper? Okay, see all the curve that you see here, right? You might be familiar with this curve. You probably see so many times from so many people. So in order to generate each of the graph here, you need to have an equation. Okay, you just don't do it like from nothing. Okay, it's just the plotting of this. But since it's the maximum we can draw on any curve is the maximum that we could use like a paper to draw is the 3D. So it's only the 3D graph that we can do that include two factors and one response here. Okay. Right. And what else? There is. Okay, see that? Okay, there's another use of actually it's the average values and also standard deviation. You see, it's the average because they are doing more than one repeat, and the standard deviation is a little error bars that they have there. And they also use t-test. Okay, they use t-test to compare if the means are different. It's obvious, right, that it is different. This one is smaller than that one, but still, okay, just to make things complete, it's safer for you to do. It's safer for you to do the t-test and show that statistically it's different. I mean, it could be important, right? The point is that if you have some graph like this, for example, if this graph become that graph, okay, and unfortunately it seems like this graph is higher than that graph, right? More than that, the value is more than that graph, that bar. But unfortunately, if you have like huge errors, they might not be significantly different. So that's one thing that you probably should think about, okay, when you are presenting your results. Okay, what else? This paper has offered nothing else. Okay, so from analyzing this paper, I just use this page because it's the most wide area. Okay, so for this paper, we see that there's a lot of stat involved. Okay, it's average value, standard deviation, the F-test, and all the R-square actually is R-square, R-square adjusted, predicted R-square. Okay, so those two are for a general representation, right? This one for modeling. That one is comparing the different. So and it could be incorporated with t-test for comparing the different. Box-Benken design is for designing what factor to be used. Anova test is for analysis of variance of the model equation. So see, one paper you have to use so many stats. So if your thesis is about this, think very well about the stats. Okay, of course you can do this in any statistical software, easy, and it just gives you the results. But yeah, for for postgrad student, I think it's worth for you to know a little bit more than undergrad, okay? Because plugging in the number, everybody can do it. Okay, interpreting it correctly is something else, and being able to judge whether this thing is good or bad is something else also.